Hello, we are back, section 8.2, and we're talking about unit vectors this time. We'll just jump right in with the definition. So what is a unit vector? As you might guess, a unit vector is any vector that has a length of 1. Any vector that has a length of 1 or a magnitude of 1, we say is a unit vector. So obviously most vectors aren't going to be unit vectors. Most vectors do not have a magnitude of just 1. But it's still helpful to us to talk about a unit vector of a different vector. So with the same direction as another vector, but with a magnitude of 1. So we're going to talk about how to find that. So let v be some vector such that its magnitude does not equal 1. In other words, v is not a unit vector. Then we can define a unit vector, u, for vector v, if the magnitude, the length of this new unit vector is 1, and u has the same direction as v. So let's stop and think for a second. If we have a vector v, its magnitude is some number that's not 1. How could I make that magnitude 1? I could divide by its magnitude, right? So if I divide by the magnitude, then I get a unit vector. I get a vector with a length of 1. So dividing by the magnitude is what we're going to do to find a unit vector that has the same direction as the vector we have. So let's just jump right into an example, because I know I can talk and talk and talk, but that doesn't mean it actually makes sense to you. So let's go through some practice problems. So consider the vector v equals 3, 4. Find a unit vector that has the same direction as vector v. So we need to start by finding the magnitude of vector v. So magnitude, Pythagorean theorem, that's 3 squared plus 4 squared. Square root of 9 plus 16, square root of 25, 5. So if I take vector v, 3, 4, and I divide each component by the magnitude, I get a unit vector. I get a vector that's pointing in the exact same direction as the original vector, except its magnitude is now 1, which is exactly what we wanted to find. So that's my answer. So looking at example 2, I need the magnitude of u, which is the square root of 5 squared plus negative 6 squared, 25 plus 36, the square root of 61, which unfortunately we can't simplify at all. To get my unit vector that has the same direction as u, I take each component and divide it by the magnitude of u. And now this we should simplify. We rationalize the denominator, multiply the numerators and denominators by the square root of 61. 5 times the square root of 61 over 61, and negative 6 root 61 over 61. This is my answer. As strange as it looks, and as unhelpful as that may seem, we just found a vector that is a unit vector. It has a magnitude or a length of 1, and it's pointing in the same direction as the vector we started with, which is what we wanted. So go ahead and try example 3 on your own. Be great practice for you. But that's really it. So that's our first learning target for this section. Incredibly straightforward. We're just dividing by the magnitude to find our length of 1 with the same direction as what we started with. Now, we can think of other unit vectors, and there are 2 special unit vectors with a length of 1 that we will talk about a lot. And we name them I and j. This is not I. It's not the imaginary number. It's just I. Yes, I know it's annoying to make that distinction, but we do in math. So I is this unit vector, and j is this unit vector. So if we check them both, we see that they have a magnitude of 1, a length of 1, except I here is going up 1. There's no horizontal component. It's just a vertical, or goodness. There is no vertical component. There is just a horizontal component. This is I. I go to the right 1, and then up and down 0. J, on the other hand, does not have a horizontal component. It only has a vertical component. I'm going up 1. So with these unit vectors, I and j, we can actually express any other vector in terms of I and j. Because if I have a vector that's 3, 4, then that's 3 i's going to the right 3, and then 4 j's going up 4. So, as you can see here, if I have a vector a, b, where a and b are the horizontal and vertical components respectively, I can write that in terms of I and j as ai plus b times j. Incredibly straightforward. So to be able to write a vector in terms of I and j, for example this, u equals, well this is a, this is b, so 5i minus 8j. That's it. It's literally all I'm asking you to do there. And you may be asking yourself, well, why do we bother doing this? Well, we'll see in just a minute, actually, what this enables us to do more easily. So we can perform the same operations with vectors in terms of I and j as we did before. So if I'm adding vectors, so in this case 2u plus 5v, this is u, this is v, 2u is still just going to be 2 times this, 6i plus 3j. 5v is going to be 5 times v, so negative 5i plus 30j. And then 2u plus 5v, I add them together. So 6i minus 5i is 1i. 3j plus, not 3, 4. I'm so sorry. So 4j plus 30j is 34j. And that ends up being my answer. Really straightforward. Same thing that we did. I keep saying that, but that's because it's true. I don't want you to be freaked out by vectors just because they look weird. Okay? It really is as simple as it looks. So example 6, I'm actually going to ask you to try yourself. Because again, I think it's good practice just to make sure that you're getting the hang of this. And instead, we're going to move on to the last thing that we're going to talk about this section. And that's, like, what if I know the magnitude, or I know the length and direction of a vector, but I don't know the horizontal component, A, or the vertical component, B? So how could I express this vector? How could I write this vector as A, B, or in terms of I and J? So just to clarify, let's take a look here. Now, say I have this vector, and I know the magnitude of the vector, so I know this length here. And I know the direction, so I know the angle. I know the angle it will make, right? That's going to tell me right away what direction I'm pointing this vector in. But I don't know this side length, B, and I don't know this side length. I don't know the horizontal component, A, or the vertical component, B. How could I find A and B from this? Well, you guessed it, that's a right triangle. And I know the angle and I know the magnitude, so the cosine of that angle is going to be adjacent A over hypotenuse, magnitude of V. If I solve for A equals magnitude of V times the cosine of theta, the direction. Similarly, sine of theta is opposite over hypotenuse. Solve for B, that vertical component, and we get the magnitude of the vector times the cosine of the direction of the angle. So in fact, those are our formulas here. If V is a vector with magnitude V, or absolute value of B, and direction theta, then we can find A and B. A is the magnitude of V times the cosine of theta. B is the magnitude of V times the sine of theta. This is the horizontal component. And this is the vertical component. And this is exactly from trig, from our last 3 units, right? Cosine is x over r, sine is y over r, except instead of x, we have a horizontal displacement or component. Instead of y, we have b, a vertical displacement or component. And instead of r, we have the magnitude of the vector. This is also the exact same that we just talked about with complex numbers in polar form. And r is now the magnitude of the vector. A and b, horizontal and vertical components, real and imaginary components. So, looking at example 7, a length of 8, so that means the magnitude of this vector is 8, a direction of 60 degrees, so theta is 60 degrees. Find the horizontal and vertical components, and then write the vector in terms of I and j. So my horizontal component, A, is going to be the magnitude of v times the cosine of theta. That's 8 times the cosine of 60 degrees, 8 times 1/2, which is 4. That means B, the vertical component, is the magnitude of the vector times cosine of theta, 8 times the, not cosine, my goodness, forgive me, sine. So 8 times the sine of 60 degrees, which is 8 times the square root of 3 over 2, or 4 square root of 3. So this vector in terms of I and j is 4, or a, I, plus b, 4 square root of 3, j. That's it. So I can find a and b if I can find a and b if I only know the magnitude and the direction of the vector, which is incredibly helpful to us, so we can actually express these vectors in terms that we can do operations with. So there's one last thing one last skill that you should be able to do in this section, and that's, given a vector, tell me what its direction is, or tell me what its magnitude is. So finding the magnitude is pretty straightforward. We've done that before. It's the Pythagorean theorem. But finding the direction, in this case of negative root 3i plus 1j, I want to find the angle. So going back here, now I know b, I know a, and I need to find theta. I know the opposite side, I know the adjacent side. It seems to me like we're going to want to use tangent of theta is b over a. This is a, this is b, so that's 1 over negative root 3. We recognize that if we unsimplify it, is 1/2 over negative root 3 over 2. This is y over x. So theta is going to be 5 pi over 6, or 150 degrees. And that's it. That's the direction this vector is pointing in. And tangent of theta is b over a, or tangent of theta is y over x. It's the same formula we've been using. We're now just applying it to something a little different with vectors. All right, I hope that was straightforward. Truly, that's why I keep saying it. And if it's not, come talk to me, please. Come ask questions. But I do hope this is making sense for you. I hope you're practicing and doing these problems that I'm asking you to, and that you're here in class and paying attention and taking advantage of those opportunities as well. So have a great day. Let me know if you have questions, and I will see you in the next section. Thank you so much.